When not working for Anchor systems, Jay is hacking away and doing stupid things in both Linux and Python. If it's a bleeding edge feature, you can be assured that Jay has played with it, written a library to use it, and deployed it into production at some point. Take it away, Jay.
Thank you very much. I'm here to talk about streaming templates with AsyncIO. You heard a bit about me, but by day I'm a systems administrator for Anchor. I do a lot of crazy things, which mainly means deploying a lot of PHP for customers into production. We are hiring. If you enjoy fixing problems at all hours of the day, please visit our website and send in your resume. Yeah. So by night, I do completely different things. Like all programmers, I work on a lot of libraries people have never heard of and will probably never use, apart from myself. The one I'm talking about here today is Wither. I don't want to talk too much about the library itself, but more about my experiences with migrating it to AsyncIO. But there's a couple other libraries I've used or written that have used AsyncIO, such as Butter, which allows you to interface to low-level features of Linux, such as iNotify and FA-Notify, and Archangel, which was a web server for AsyncIO. But please feel free to ignore them. They're probably they're not really production ready. But I have had a bit of experience with writing AsyncIO code. So yeah, what does this talk about? Definitely not talking about my templating library, as I said beforehand. This is about something slightly different use of AsyncIO. I didn't want to talk about just writing another socket server. I wanted to talk about something, not your standard usage of AsyncIO. In this case, it's how to stream templates incrementally out to a client. I really did want to point out the good and bad points of AsyncIO. As it's not all roses, there are a couple of annoying things, nothing too major, luckily. And I want to give people some inspiration to use AsyncIO in their own project, because I think it's great, and it's annoying that we've had so many implementations up till now that are not compatible with each other, and unfortunately not everyone's using Twisted. So what is Wither? Wither was originally written for Python 2.7. I just learned about context managers, which is probably not a good idea. And I was also looking at templating libraries at the moment. The one thing I did notice about context managers, the context manager protocol, is that they have an entry point, some code in the middle, and then an exit, or code that gets executed at the end. And as I said, I was playing around with templating and trying to choose a templating language for my website. And I noticed there's a very, very similar parallel between that and XML. So XML, of course, has a start tag, an end tag, and does something in the middle. And I really started wondering, was there some way that I could join these together or use them together? And what ended up happening was I ended up using Python as an XML generation language that looks very, very similar. It basically ends up looking like a white space version of XML. So as an example, as you can see there, create a root node. We've got the with statement there. That's the implements context manager protocol. Turn that into a string. Get your HTML back. A lot of services think that's actually minified, which is kind of funny. But yeah, so rather simple. White space sensitive XML using Python. Eventually, I wanted to start migrating to Python 3. And I needed something really simple to be able to migrate and just see how bad the string versus bytes issue was and how it's going to affect my other code. So Wither made a perfect test candidate for that. The original implementation of Wither was actually kind of nice and small. I wouldn't say elegant, but fairly clean. It's a very, very horrible abuse of syntax, as you saw earlier. And I had toyed with the idea of putting blocking calls in there, with the idea that I'd eventually wire it up to something like Twisted or G-Event. So I checked a couple of yields in there and saw what happened, but I'd have a lot of logic outside the template itself to do the actual translation, which didn't work very well. And then AsyncIO came out, which basically solved entire classes of problems. I no longer had to worry about an event loop. I no longer had to worry about the APIs I'd use and the best way to express that, to have the blocking behavior in my template rendering. so that I didn't have to spin up threads or anything like that. And I think the biggest win from this was allowed me to mix and match with other asynchronous I/O code. One of the biggest issues I've seen with G-Event and Twisted is that you have libraries written to use them, but they're not really compatible with each other. And I'm hoping that asynchronous I/O solves this, that we end up having, you no longer have to worry about whether or not the asynchronous I/O library you're using is compatible with the library to talk to your MySQL server. You can just compose them together. So, I mean, why would you want to stream templates out to a client? As I said, we've got a lot of PHP code, and a lot of them try and game web page test in Google, because the Google especially ranks your page based, or your page rank is influenced by how quickly you can get data out to the client. And so there's a lot of PHP developers that send out a single blank space byte in an effort to get their page rank up. And I really began to wonder if it was possible to do this with Python, but not in an attempt to cheat Google, but to actually get content out to the client faster. The other reason you want to do this is the faster you can get the data to the client, the faster they can start rendering it. So you're no longer blocked on the server returning the entire request and then rendering it. You can render it on the client side and the server side at the same time. The implementation itself, or what I had to do to make this all work was, if you've ever used a templating language, you're probably familiar with how you interact with these. You have a template object, you call .render on it. You pass it in the dictionary, which is your environment. It does substitution. You get a string back. This isn't going to really work well with incremental rendering and streaming that out to the client, because, of course, you can't wait till you get to the end and get one massive string. You actually do need to get parts of it and send that out to the client. So my solution here was to just insert a pipe, or a queue in this case. So now my template.render function just returns a queue, which when I was doing a lot of asynchronous I/O, I ended up using the queue object quite a bit and reused it. I found it's a very, very valuable primitive to be familiar with in asynchronous I/O, as it formed the basis of linking a lot of my code together. So yeah, you now you call the render, you get your pipe back, read bytes off the pipe, send that out to the client, and you get streaming for free. The template can block all at once, and AsyncIO just takes care of the details. I don't really have to worry about that anymore, or if I have threads and whether or not how many threads I have. It's just handled for me. I did want to talk about performance, because I actually get asked this a lot at work. I don't know if anyone's used Ginger 2. I'm assuming a lot of people have. Has anyone actually ever benchmarked it before? It's incredibly quick. If you're doing anything pure Python, which with or what is pure Python, you're not going to be able to catch up to it at all. It is one of the fastest templating libraries I've used. I also got beaten by Wither. This was actually quite surprising. I was expecting asynchronous I/O to be quick. Now, these were trivial examples, so I take it with a bit of a grain of salt, but the performance overhead of asynchronous I/O is not going to be the dominating factor in your application. This was just a very, very trivial two-line example, and I was mainly dominated by the function call stuff here. So the generators are a lot heavier than a function call. Wither itself was 1 or 2 function calls. Wither 3 was a couple of generators and a couple of function calls, so immediately you lose there. In hindsight, that made a lot of sense. So I guess the takeaway from this is that if you're going to be doing asynchronous I/O, you really don't want to be doing a lot of context switching on trivial things. You want to do a certain amount of work, or quite a bit of work before you swap, just to get rid of that overhead and make sure you're not dominated by that switching overhead in the asynchronous I/O. So if you're looking to make a high-performance DNS server that's pushing out 10 gigabits per second, and you're doing trivial processing, perhaps you should be looking at other options, using the callback interface directly rather than the higher level yield from interface. just to try and eliminate some of that overhead. But with a 3 being slow might actually not be that bad. I might actually possibly win with slow backends. So if I have a MySQL server that's taking 200 milliseconds to run a query, because I'm pulling out a lot of data, and I'm blocked on that, but that's halfway through the page rendering, then I can send half the page back to the client and have that rendered client, that half of the page rendered on the client side earlier, and hopefully win by having the total page load time reduced. So I'm interested to play with this a bit more and just see how much of a win that is. So I learned a couple of things when I started playing with asynchronous I/O. You really want to keep your code small and simple. It's very, very easy for things to go wrong. The nice thing about the high-level interface that gives you the yield from is it makes your code seem like a normal straight-line code. You don't have to worry about callbacks or anything, which is the one thing that always turned me off with Twisted. One other piece of advice that I found is you want to keep your coroutines or your actual tasks very, very simple and only do one thing. At one point I was reading data in one direction and reading it and writing it in the other direction in the same coroutine or task. And then I realized I could split that up into 2 coroutines, and the implementation became a lot simpler and a lot easier to diagnose. I ended up having a lot of really odd blocking behavior where if one side was blocking on a read, the data going the other direction wasn't going across the wire until data came in from the other side. And yeah, just try and avoid that. Just basically try and make your coroutines focus on a single specific task. So as you can see, just make a coroutine, copies data in only one direction rather than both directions, and just spin up 2 of them. One other interesting thing was in the syntax, you've got the yield from, which indicates a point where your code is actually going to block. Between those yield points, it's like having an implicit lock or the GIL. So if you have to do an update on 2 lists, you don't have to take a lock and protect those 2 lists from having updates to them. You've got an implicit lock. Of course, if you have blocking code in between those 2 updates, you are still going to have to take a lock. But it's actually amazing how much this simplifies your code. I tend to find these updates are normally in between the yield points. And not having to take a lock or worrying about locking concerns really, really made my code quite a bit simpler. So that's one of the things I do love about asynchronous I/O. I might also point out that if you're trying to learn asynchronous I/O, the PEP, or the Python enhancement proposal, is 3156. This is actually quite readable. It's probably one of the best sources for learning asynchronous I/O. The documentation I found in the standard lib is work in progress level. I'd take that as the authoritative source, and then as a second point of information, possibly the source code, because as I'll show later, it's actually quite readable. But the one thing about that engineering proposal is it makes a distinction between a high-level and a low-level interface. So with your own code, I found you really also want to have a low-level and a high-level interface, where you've got a low-level interface that's doing the data transforms and doing basic error checking, and then a high-level interface that's doing the actual logic and presenting an API to the user that they expect and is nice and easy to use. So splitting up those concerns is always a good idea. I did learn a lot of horrible things. I was trying to do things that were not really the typical use case of asynchronous I/O, and you'll see a lot of them listed here. I was trying to make queue raise stop iteration for reasons I don't really want to go into. And the reasons I won't go into them is because it's a bad idea. You really just don't want to do it. Almost consider never raise stop iteration from any of your programs unless it's a standard generator. If you're blocking on it with yield from, it's just going to cause issues. So consider it a reserved keyword or something like that, and only for AsyncIO's use. The other one is that you never actually want to be using yield in your code, always yield from. If you see yield in your code and it's a coroutine or something like that, it's most likely a mistake. There are a couple of reasons why you might want to do that. But if you want to do that, you'll know ahead of time that you want to do that. If you have to ask whether or not you need it, you definitely don't. The other thing to keep in mind is that generators and iterators are not interchangeable in asynchronous I/O. Once again, this seemed obvious in hindsight once I'd actually gone off and done it, or did it, but tried it. But it wasn't explicitly documented, and it was something I thought I could get away with. The asynchronous I/O code uses a is generator, and is generator function to check if you've actually returned a generator, and it's actually incredibly hard to bypass this. I actually haven't found a way to do it that's nice. The other thing to keep in mind is that generator objects are not mutable, and that's the reason for why I was looking into a couple of things above. I basically wanted to be able to register a callback on a coroutine or a function, and that doesn't work because the generator objects are read-only. So the cheat here is you, of course, create a class and put your coroutine in the under call, and that allows you to register a whole lot of methods and still get access to self to pull out the list of callbacks that you need to trigger when you block. So it's not all bad. I actually like asynchronous I/O good. The things I'm complaining about are all minor, and it's just me trying to push the limits of asynchronous I/O. The code base itself was incredibly approachable. I thought it was going to be this really hideously complex thing that took a master to understand. But after reading through the code, I found it was actually quite simple. Once you understand that between two yield points or yield from points, you're going to have exclusive access to the Python environment and not be taken off the CPU, it starts to make a lot of sense why there's no locks and things in there. I mean, to the point where I reused the asynchronous I/O queue object as a basis for a lot of my code when I needed to do fan in or fan out of events. The asynchronous IO.queue is a AsyncIO compatible queue object, just like queue.queue. And it really is, if you want to understand asynchronous I/O or get involved with the code base and possibly submit patches upstream, I'd recommend starting there because it's rather elegant and something you can easily reuse in your own code and modify as required. One of the nice things was that PDB just works. This was a bit unexpected, but it makes a lot of sense because the exceptions come out exactly where you expect them to, just like they would if it was normal blocking code. And that's just due to the futures and how they've been implemented. They'll actually raise the exception in the correct place, which is just wonderful. I didn't have to learn any additional debugging techniques to be able to diagnose my asynchronous I/O code. There's a couple of things I would like, and I'll talk about them later. But the general tools available for debugging Python work just as well for debugging asynchronous I/O code. So I was very, very happy about that. One of the unexpected wins I found was that parsers for protocols are really, really easy to write. I don't know if anyone's seen David Beasley's coroutines part 3 talk. He does touch on this, where he's got delegating to subparsers using yield from. I decided to play around with that, but rather than parse strings throughout the entire stack, use read with asynchronous I/O. The nice thing about this is it turned my parsers into streaming parsers, which was just absolutely wonderful. And the ability to delegate to subparsers with this, if they're all just using asynchronous I/O, was great. So I could make, for example, a Python parser that recognized a specific type of string that allowed me to inline JavaScript and get the full parse tree for a JavaScript object if I wanted to. And as long as someone else has written that JavaScript parser, I can just delegate to that and get the full tree back. So that was great. Asynchronous I/O takes a lot of care of a lot of the details there, such as buffering, which was really, really nice. There are some bad parts I touched in the previous talk. This is essentially cooperative multitasking. I don't know if anyone's ever encountered the issues with this before, but if you've got a CPU-heavy task and you don't block with the yield from, no other process is going to run. So if you have a task that has to be run on a regular basis and you're doing CPU-heavy work, you might miss the time slot for that to be run. It will actually get run when the yield from happens, but it might not happen when you expect it to, which can be a bit unintuitive. So if you need to do something like that, I recommend splitting it off into a sub-process and let the actual OS manage the scheduling of that, or find some other tricks, such as putting it into a queue and let Celery process it or something like that. So anything that's CPU heavy is not a good match for asynchronous I/O. You really want to use the traditional methods to solve that that Python has available. The other thing is that tasks get processed in order that they get added or scheduled. There's no high priority task. I have seen some implementations with stackless Python, especially, where they had like a high priority list of tasklets to be run in low priority. That's not a good idea in asynchronous I/O. The PEP actually says that things get processed in order, and you want to obey that. You really don't want to violate any of these assumptions, because odd things will happen. This may seem like a minor one, but I've seen in practice that this can actually burn you with priority inversion and that sort of stuff. So the other thing, I'll be touching on this multiple times, is I returned a queue from my templating library. That's effectively decoupled them. So I've decoupled the sending of the data to the client and the rendering of the template itself. Now, if the template rendering dies, I have no way to communicate that it's died over the wire back to the process sending out to the client. And this turns out to be actually a fairly large issue, because that task that's sending out to the client will actually block forever waiting for data. And it's going to keep that TCP socket to the client open as well, because the OS is maintaining the connection state there, and until the application explicitly closes it, that's going to continue on forever. So there's a couple of ways to solve that. You can solve that with a timeout, but I'm currently working out how to do some sort of scheduling or supervision of tasks. So I can say, these tasks, if any one of them dies, kill the entire stack. So very similar to Erlang. I did say PDB worked, and you didn't need any additional techniques to debug. That was a bit of a white lie. You don't need any additional techniques. There are some things you do want. Being able to get a list of tasks that are running and what they're blocked on is incredibly handy. It took me a while to actually discover that one of my rendering process had died, longer than I actually care to admit. What I found, though, that once you've got a list of running tasks, as long as you've got a very, very simple test case, it's very, very easy to track down these issues. So I think there's two takeaways from that, in that we need to look into process supervision, and we need to look into some slightly better debugging techniques just to enhance asynchronous I/O a bit. And one of the other things that I found a bit irritating, because I wasn't expecting it, was stack traces contain a bit of noise from the asynchronous I/O library. I was expecting to see all my code there and none of the asynchronous I/O. And when I was looking at stack trace, I started working up the trace and then saw a whole lot of function calls I wasn't expecting. And it really, really threw me. So you get stack traces that look like this. It's a rather simple example. As you can see, I've got my code down the bottom here, wither, and then I've got a couple of lines of asynchronous I/O. I actually didn't look any further up, and then I would have seen my original wither code. So if you do encounter stack traces and they don't look exact, or you can't find the flow of execution that you think should be there, keep on going up the stack until you find your code. Because it might just be that there's a couple of levels of asynchronous I/O code in there. It was a basic mistake, but it did catch me out. So now, if you're probably wondering what libraries are available. This was just a quick list from the cheese shop. The amount of packages that are growing for the amount of packages coming in for asynchronous I/O is growing daily. I'm actually surprised at the rate that they're increasing by. Postgres is available already. Redis. That SSH library I'd like to specifically point out. That's both an SSH server and a client library. So if you want to embed an SSH server in your application, say for debugging the list of tasks that are alive, It's about 5 lines, and I've played with it, and it's a lot of fun. I can't wait to do a bit more with that. I do also want to point out that FA Notify and iNotify and SignalFD and TimerFD, for full disclosure, is a library I've worked on called Butter. And there's AO.DNS and a couple other things. So the other DNS is probably another thing, another library you might want to be familiar with, because currently when you've got called get host by name under the AsyncIO library, it actually spins up another thread and does that in a separate thread because that call is actually blocking. So if you want full AsyncIO DNS, you will have to look into AsyncIO DNS. I've touched on it briefly so far in the talk. There are a couple of things that are missing that I would like to see. Erlang has had to face this issue before. They developed the OTP suite of facilities to enhance your application. So if one process dies, they all die. It'd be nice to either automatically restart them or have them all die to get all the tasks, all the related tasks processing a request die at once. The one issue I had with unit testing this is that if I had something die unexpectedly, then and I had something waiting for data to come in, that would never return. So it's very true we would write, but a sort of timeout to limit the amount of time a task can be running is something very, very handy for unit testing. Otherwise, you might lock up your continuous integration environment if you don't have a limit on time limit on test runs already in the CI program. Netflix developed a very, very good library called Hystrix. It introduced a lot of interesting primitives to make your app a lot more robust. The two nice ones are @retry, to automatically retry transactions if they fail. But probably the most important one is @short-circuit. Short circuit, which could quite easily be made into a decorator. And this basically allows you to, when a service is not responding or not responding in a timely manner, just short circuit that and fail fast and return a default value so that your code doesn't, or your page doesn't take too long to render. There's actually a couple of implementations on the Cheese Shop, but none of them are asynchronous I/O compatible, and all of them had, you had to buy into how they did I/O and threading and all of that, which was a big issue. So a generic solution would be kind of nice. As I mentioned, you can embed SSH servers or Telnet servers into your application, which is really, really cool. You can back that with PDB or just list the tasks that are running. And it'd be really nice if there was a library you could just drop in, import a module, call a function, and have that debugging functionality available to you. I do want to point out that the current Whiskey spec is not asynchronous I/O compatible. You can't do blocking behavior in Whiskey request. I did mention Archangel at the beginning. It's got a specification in there for an asynchronous I/O compatible Whiskey spec called Twig. If anyone is interested in that area, I recommend grabbing that as a base and stealing all credit for it. I'm working on it just incredibly slowly, but it's something I would like to see solved. Because there's a lot of directions you could go with this, and it'd be nice if we just had one standard rather than 3 or 4 different incompatible implementations. And finally, an Encurse's library would be nice. It's wouldn't be too hard to write. I'll probably end up writing it sometime in the next 6 months. But if you're looking for an easy project, this is probably the easiest one to tackle on that list. Most of these are actually fairly simple once you understand asynchronous I/O. So yeah, if you're looking for something interesting to cut your teeth on asynchronous I/O, you might want to try having a look at these libraries. Finally, thank you, and yeah. So any questions?
So you mentioned you have to use yield from and not yield, right? What is the context of that? What if you use a library in one of your coroutines that itself uses yield? Is that okay? Is that not okay?
Yeah, it's more of general advice rather than anything. If you're doing pure asynchronous I/O code, you shouldn't really ever see yield in there. If you have a reason to use yield, then of course use yield. So if you're trying to patch things together, yes, yield's a good idea. I've actually used yield as a trampoline so that I could intercept the blocking behavior of the event loop and then do the callback, which I touched on or mentioned briefly. But it's just not something you should see in general day-to-day code. If you need it, there's a reason for it. Otherwise, don't touch it. Any other questions? Excellent. Okay. Thanks for that.